So now moving on with chapter 4, and we learned about Newton's first law, where it states that if no net force is acting on an object at rest, the object remains at rest, and if the object is moving, it continues moving with constant speed in a straight line. But when we apply force on an object, Newton saw that the object's velocity changes. Hence, a net force is generated, and that net force, according to Newton's law, as we learned previously, is given by F net is equal to mass times acceleration. So you apply force on an object, and there will be some forces acting on it. There will be force of push, and there can be forces of friction in the opposite direction, and the object moves with a net force. So the net force is always forward minus the backward, which is the force of friction. So sum of all the forces together makes the net force. And because force is a vector and it has a direction, so if Fp is positive, force of friction is in the opposite direction, hence the negative sign for it. That is equivalent to mass times acceleration. For example, in this case, the net force is given already. So he's not giving you the force of push or force of friction because we have not talked about it yet. So he gives us net force already, which means it's sum of all the forces, and it's equivalent to 51 newtons. And at what rate does the lawnmower accelerate to the right? So we need to know the mass for this one. So for example, if the mass is given equivalent to 50 kgs, so I can find out the acceleration, because F net is equivalent to mass times acceleration. A will be equivalent to F net over mass. So you got to plug in 51, or probably I should take 51 kgs to make things easier for myself. 51 newtons is the net force. 51 kgs is the mass. Therefore, acceleration will be 1 meter per second square. So this is how you work on these simple Newton's second law of motion problems. But let's work on one more problem which is related to Newton's law and kinematics together. So now you are going to combine kinematics and Newton's laws together to solve a problem. So for example, if we have a simplified model of a mammalian heart, and at each pulse approximately 20 grams of blood is accelerated. So when we say accelerated, that means it gives you the initial velocity and the final velocity, and the time is also given. So what is the magnitude of force exerted by the heart muscle? So basically he's asking you to find out the force exerted by the heart muscle. From Newton's law, we know that net force is equivalent to mass times acceleration. In this case, the net force is simply the force that is applied on the heart. So we have to find that. I know the mass of the blood. So M that is pumped is 20 grams. So you should go ahead and convert it into kgs. 1 kg divided by 1000 grams. The grams and grams will get cancelled. So make sure you do the conversions beforehand. I can even write it like this. If you don't want to put it in the decimal form, we can later on substitute. But one thing he's giving us is initial velocity, 0.25 meters per second. Final velocity, 0.35 meters per second, and time during which this entire process is happening is 10.10 seconds. So since you need the acceleration, so if you remember the kinematic equations for one-dimensional motion, v is equal to v naught plus at will give you the acceleration. So go ahead and find out what the acceleration is from this equation. You can stop my video and work on it and then replay once you're done. So v is equivalent to v naught plus at, rearrange the terms, and your acceleration, you can also find simply write the definition of acceleration, which is v minus v naught over t. So you get 0.35 minus 0.25 whole divided by 0.10, which should come out to be equivalent to 1.0 meters per second square. Now that I have acceleration and I already know the mass, I can go ahead and find the force exerted by the heart muscle, which will be equivalent to mass. I kept the mass as 20 cross 10 raised per minus 3 kgs. You can go ahead and divide 20 by 1000, and you can even have 0.002. That's also fine, but this is also fine if you leave it like this. And then multiplied by 1.0 meters per second square will give you the answer in newtons. Kg meter per second square is in newtons, and when you work on it, it comes out to be 0.02 newtons force, which is a small force. Go ahead and check the sig fig thing also, because we have 2 sig figs given over here as the least. So our final answer is also in 2 sig fig form. Next, you can also work on this. What is the average force required to stop a 950 kg car in 8.0 seconds if the car is traveling at 95 kilometers per hour? So if we have to stop the car, okay? So you are going to sketch your scenario. What average force? So for example, the car is moving and you want to stop the car. Okay, so what is the average force that you need to stop the car? What are the stats that are given? The mass of the car is 950 kgs. And since you are going to stop the car, the final velocity must be 0. The initial velocity is 95 kilometers per hour, which we are going to go ahead and convert. So v naught equivalent to 95 kilometers per hour. You're going for 1 hour, there is 3,600 seconds. And for 95 kilometers, you multiply by 1,000 meters. So once you work on this, this velocity comes out to be 26.39 meters per second. I won't use the 2 sig fig thing yet, because this is not the final answer that we are looking for. We'll use it in its entire form, so that when we find the force, we can use the 2 sig fig thing. So now I know the v. I can go ahead and find out the acceleration. Acceleration is v minus v naught over t. Time is given this as 8.0 seconds. So you go ahead and substitute the values. Obviously the acceleration will be negative because we are trying to stop it. So divided by 0.8 will give us acceleration as negative value, and that comes out to be minus 3.299 meters per second square. Again, I reiterate that when I'm solving these problems in the video, it is always a good idea to work on them yourself, pause the video, and then rework. It will give you greater satisfaction if you're working on these problems yourself. And then checking the answer. So now that I have A, I can go ahead and find out the average force, which is equivalent to mass times my average acceleration that we determined. Mass times acceleration average. The mass was 950 kg car multiplied by minus 3.299 meters per second square. You'll get a negative number. That's because in order to stop the car, you must have to apply the force in the opposite direction. So you will get minus, if you work on this, this is minus 3134 Newton. But I know that we learned about sig fig and stuff, so we are supposed to answer the question in the form of the least sig fig. So the least sig fig is 2, just as you can see, even the least sig fig is 2 everywhere. But the best way to write it in the form of least sig fig will be to approximate it. Minus 3100 newtons will be the least sig fig value for the average force. Okay, so now let's go and talk about another concept, that is weight, the force of gravity, and the normal force. So you were talking about mass and force applied in the horizontal direction. What about the forces in the downward direction, which is the weight of the object? The weight is always acting downwards because of the acceleration due to gravity. And Galileo claimed that all objects dropped near the surface of the earth would fall with same acceleration g, and if air resistance was negligible, of course. So the force that causes this acceleration to make the objects fall down is force of gravity, or gravitational force, and that gravitational force is given by mass times acceleration due to gravity, which we also call weight. Okay, so and normally they write it as f of g. In our notations, we write it as force due to the gravity g, which is nothing but mass times gravity, indicating that it is the gravitational force. And if you know your mass, you multiply it by g, that is 9.80, so you get the weight as in the form of newtons. So weight is the force exerted on an object by gravity close to the surface. The gravitational force is constant and is very nearly constant and is given by the weight. The units still stay as newtons, just as we described. The units of weight are newtons because it's mass multiplied by mass in kgs, acceleration in meter per second square. Together, all of this makes 1 Newton. So the force of gravity acts on an object when it is falling. When an object is at rest or on the earth, the gravitational force on it does not disappear. We still have it. Because if you are on earth, whether you're moving, whether you're falling, whether you're sleeping or walking, your weight still stays the same, and you can measure your weight by spring scale, and the same force continues to act all over wherever you're going. So why doesn't the object move then if the weight is always there? So from Newton's second law, the net force on an object needs to remain, for an object at rest, the net force must be 0. Even if the gravitational force is acting, somehow the net force acting on you must be 0. That's why you're not able to move. And that net force is the sum of all the forces. So for example, we have, we'll come to that. If we have a textbook on the table and it's lying at rest, but why isn't it falling through, even if it has force of gravity acting downward? But there's a force acting in the opposite direction, which we call the force by the table exerting on the book, and you'll learn that we call it as normal force, and that is balancing it, and with the result the object stays at rest. We'll talk about that in a short while. So let's work on one of the problems where we are going to find out the weight of different objects at different places. The weight of an object changes with place. So your weight changes because of not because of the mass. Mass remains same everywhere, even if you go to Mars, Moon, Jupiter. Mars is possible now. if you have been watching Perseverance landing. So very soon we'll be having flights to Mars happening soon. Okay, so it's the value of g that changes, and hence the weight changes. So it's interesting to find out what different places will have the weight. So for example, on Earth, if the weight of the astronaut was given as, if the mass is given as Fg, which is the weight on Earth for part 1, will be mass of the astronaut multiplied by the acceleration due to gravity on Earth. When you substitute 68 kgs and multiply it by 9.8 meters per second square, that comes out to be 670 newtons. So the astronaut on Earth weighs 670 newtons. The same astronaut, when he goes to Moon, the acceleration due to gravity drops, and hence the weight will change on Moon. So it will be mass times acceleration due to gravity on Moon. So that becomes 68 kgs multiplied by 1.7 meters per second squared, equivalent to 120 Newton. So you see that how weight changes from place to place, although mass remains same. Same way, we can find the weight on Mars, where the acceleration due to gravity is 3.7 meters per second square, and it's still lesser than Earth. So the weight should obviously be lesser. So we have m times g on Mars, and that will be 68 kgs multiplied by 3.7 meters per second square. And once you work on this, again, you should stop the video and work on them yourself, and then play the videos to check the answers. But what happens in outer space when you are traveling with constant velocity? That means there is no acceleration in place. When you're traveling with constant velocity, a should be 0. So there's literal weightlessness. So outer space, constant acceleration means 0, hence weight is 0. Apparent weight is 0. We'll talk about that later, that there are still forces acting on it, but the apparent weight or the net force works as 0. The most important part in chapter 4 is going to be solving problems and the free body diagrams, which we in short call FBD in short form, free body diagrams. What are free body diagrams? Free body diagrams are the representation of forces in the form of vector. So if I have a vector and I'm pushing, so I can name it as force of push. And if there is a force of friction acting in the opposite direction, I'll call it force of friction. If there's a bucket and it is lifted with a rope, or if there is a flower pot hanging from a rail, so there will be force acting in the upward direction, which is tension. So it is represented by a vector f of t. And there's weight acting always in the downward direction, we call it as Fg. So how do we work with problems when we represent forces in the form of vectors? Okay, and then we talk about net forces acting on it, and this was the interpretation given by Newton's second law. So let us look at a free body diagram. It's a diagram. Okay, so this shows the scenario for you that two people are trying to push it, and their combined effect, each one of them is applying 275 newtons, and another one is applying 395 newtons force to move the car. But there is an opposing force of 560 newton, just as I said. So in order to draw a free body diagram, the first thing we do is we do not draw a car anymore. We draw a dot for a car. And for forces, we draw vectors. So you see that if 275 Newton is given and 375 Newton is given, you see the vector difference. The 275 vector is shorter compared to 395 vector. So vector length represents the magnitude, arrow represents the direction, and 560 is bigger than 275 and 395, and that is why the length of the arrow is longer for 560. But because it's acting in the opposite direction, we represent it in the opposite direction. So we always draw x and y axes, and then we show our forces in terms of whether it's a horizontal force or whether it is a vertical force. So for example, in this case, you saw the scenario here. What is the net force now acting on this? To find the net force, we will add up all the forces. And you see, because this direction is positive, this direction is negative, 275 and 395 are acting in positive direction, while as 560 is acting in the negative x direction. That is why we chose it as minus, and the sum of all of them then counts as net force. This gives me F net. You can either write it F net, or you can write it summation of all the forces. I prefer to write F net, and is directed along the x direction. If your answer came out positive, that means the object has more residual or net force in the positive x direction. If this value had come out negative, that means the opposite force was stronger than the combined force of push by these two people. And if we know the mass of this object, we can also find the acceleration. So if the mass of the car is 1,850 kgs, then with the help of Newton's second law, I can find the acceleration. See that he has written F of summation. You can also write this as F net. They mean the same thing. Some books show F net, some books show summation. It really doesn't matter as long as you know we are finding the net forces, which is the sum of all the forces. So you had already calculated this before. You divide it by mass, because F net is equivalent to mass times acceleration. By rearranging the terms, you are able to find the acceleration. Now, whenever we are finding free body whenever we are working on the problems, if there are forces acting in the x direction, there will be forces also. Sometimes it so happens there will be forces also acting in the y direction. So how do we find then, how do we solve those problems? Well, we first find the net forces in the x direction, then we find the next net forces in the y direction, and then find the resultant force. So resultant, just like resultant velocity in projectile motion you found, we find fx square. If we find fy square, sorry, not the resultant. The forces are, the net force is the combination of net force in the x direction plus the net force in y direction. You can even put summation here, or the net forces. If you have to find the magnitude of the force, net force, then you can square root them, fx square plus fy square. And if you have to find the angle between them, you'll go ahead and do tangent inverse f of y over f of x. Same way you did for vectors. So anytime we have to find the magnitude, we should know its x component, we should know its y component, and if you have to find the direction, you can use tan inverse formula to get the magnitude. Now, trying to find out how to do the free body diagramming. You just saw an example of a car being pushed in the positive x direction and it had an opposing force. How about looking at examples which show forces in the upward direction. So there is a cinder block or a block sitting on the table, but it's not moving, it's at rest. There are forces acting in the downward direction, which we also call Fg. Fg or W is the same, which is the force due to the gravity and is the weight of the block. But there is an opposite force that acts on the resting block, which is given by Fn and is called normal force. It always acts perpendicular to the object. Just as the definition says, normal force is one of the component of force that a surface. So if an object is suspended in air, it does not have a normal force. If your laptop is sitting on the table at rest, it has normal force. But if something is hanging in air, it does not have normal force. For a normal force to be exerted, the object has to be in contact with the surface, and the force acts always perpendicular to the surface. So that's why it's called normal. Normal means perpendicular. And when an object is at rest, then net forces, this is your net force, and it's in the y direction. Remember, this is horizontal, this is not horizontal, this is vertical. So is equivalent to mass times acceleration, but the object is at rest, so there is no net force acting on it. But the net force is equivalent to top one is positive minus downwards one negative is equivalent to 0. That means normal force is equivalent to force due to gravity. So they are balanced. And that is why when you are resting on the chair, you are not falling down. When you're sleeping, you still have weight Fg, because there is normal force balancing the force of gravity, and you are not accelerating in any direction. This is one more good example of showing how many different forces are acting on the child sitting in this wagon, where two people are exerting force. So it's the same example that I showed for the car, and here we are trying to push two. It seems that the dad is sitting in the, and the child is pushing the dad, and the mother is also pushing the dad. Fun scenario. All right, so when we push it, there are, how many forces are acting? F1, the little girl. F2 is exerted by woman, and the force of friction is acting in the opposite direction. So watch the arrows, and normal force is acting in the upward direction, and the weight is acting in the downward direction. Some textbooks write weight as W, so you should not worry about that. It can be, we will follow one system, because I took this picture from some other book, because I like the example. It showed all the vectors on it. So now free body diagram is, for this wagon, we just represent a dot, total mass of the wagon. So and then we represent all the other forces. See the normal force, we drew we drew y, x, y prime, and x prime, and we represented our dot here. Let me change the color. And there are two forces acting in this direction, so we put one F2, then we had another vector F1, we have normal force in the upward direction, we have weight. The length of the normal force and the weight is equal, because they are balancing. The object is not sinking into the earth, it's not accelerating in the vertical direction, it's only accelerating in the horizontal direction, and there is a tiny frictional force also given. Okay, so this will help us create the foundation for solving problems. And same way, we have another example where one person is only exerting force, but the scenario is still same. And understanding force vectors for this, we saw an example like this. You are applying force, and for this one, you're applying force on the ball and the ball moves forward with acceleration. And in the second scenario, the person is pushing the car. It has an acceleration because there is a force of push. There might be force of friction in the opposite direction, but we are ignoring that in this example. It's only to show you the different types of forces that are acting. So similarly, if you have a bag or a package which you want to lift, while you are lifting, it's the force of the hand that is acting in the upward direction. The normal force ceases because now it is not in contact. In this example, it is not in contact with the table. But once you put it on the table, the normal force will start acting, and the normal force and the weight will be balanced, and that's why there is no acceleration. Acceleration only happens if there is imbalance of force. And if there is no imbalance, the object stays at rest. So that's the basic foundation of these net force problems. And in this scenario, you can try to understand the problem is not given, but you have to find out what is happening in this scenario. There is a block on the table, and the weight of the block is given by 15 newtons, just as you can see. You can write Fg also for this. And there are two forces acting on this in the downward direction. The force of the hand that is pressing it down, but there is a normal force also acting in the upward direction, which is trying to balance it in such a way that the object is not accelerating downwards. So the net force must be zero. This means we are applying Newton's law that net force is equal to mass times acceleration. But since there is no acceleration, the object is not sinking in or falling down, acceleration is zero. So you can write net forces are equivalent to zero. But what are those net forces? The normal force, the applied force, the weight. This will help you find out what is the normal force acting on the block. You can find different forces if you are not given. In the second case, same scenario. What if instead of the hand pressing down, I have an additional block, additional force pulling it up? So the arrow is now in the upward direction. So normal force is becoming lesser because now there is an additional force in the upward direction. So see how we had minus 11 in this case because it was downwards, but now we are putting it as plus 11 because it's acting in the upward direction. The same XY strategy is applied here. Positive in the upward direction for Y, positive in the positive X direction, and negative downwards and sideways. So minus 15 is still the weight, and you find out that when you are trying to lift an object from the floor with the help of whether a help of rope or with the help of hands, you reduce the normal force. And if it is simply lying down, you increase the normal force is higher. So in this case, you see that the normal force was 26 newtons. You are helping it sit on the floor rather than in the second scenario where you are helping it being lifted off the floor, with the result normal force ceases. Again, normal force ceases if the contact surface is no longer there. So contact surface is important for normal force to be experienced. A good example to understand this is for free body diagramming purpose. Look at this scenario. These are all the forces in the in the Y direction, and we'll try to understand them scene by scene. So in scene number 1, there's a box that is sitting on the table and it is at rest. So normal force vector is shown in the upward direction. The weight, which we normally call Fg, it would be good to call it Fg. In our future, we'll we'll denote it as Fg. Fg is equivalent to mass times gravity, it's the weight. But since the object is not moving, we have the y direction force, means Fn is equal to mg, and that is the weight of the object, the normal force and the weight balance. But same example that I showed you behind, now if I'm applying 40 Newton force in the downward direction, the net force in y direction becomes still 0 because it's not sinking in, just as I said. Same example exactly. The net force, mass times acceleration in y direction, it's not accelerating. So normal force is in the upward direction, but this force is in the downward direction, the force by the hand. And what else is in the downward direction? Mg is in the downward direction, and together all of them equivalent to 0. If I know the mass of the block, I know the acceleration due to gravity, I can find the normal force. So let us say the mass is 10 kgs. So in this case, the normal force will be 10 multiplied by 9.8, which will be equivalent to how much? 98 newtons. But what happens if I press it down? If I press it down, that means your normal force is going to be mg plus 40 newtons. That is, to the 98, I will add 40 and it increases. So how much does it become? 138 newtons. 138 newtons. But what happens in this scenario? When I'm pulling on the object, now the force, this normal force has an additional companion in the upward direction, that is this pulling force of 40 newtons. So your Fn, it's still not lifted. If it was being lifted, it would get an acceleration. You would see it lifted off the ground. So the net force is still 0, but Fn is equivalent to mg minus 40 newtons. And you know that now it will weigh less. Okay, so it shows the normal force is reduced and it becomes 58 newtons. So when it is simply lying, the actual normal force is actually equal to the weight. When additional force is applied on it in the downward direction, the normal force increases, and if you are applying more force in the upward y direction, then the normal force reduces. And finally, if I apply ask yourself a question that if I apply 60 Newton force in the upward direction, what will happen to the box? So any force greater than this, if I apply in the upward direction, will make the block move. So you will be able to move it and the normal force will become 0. Because we have to remember for normal force that there needs to be force greater than it, there needs to be a surface in contact. So same block now with mass m into g is 98 newtons, which we already know. Normal force has ceased. The force of push exceeded the normal force because now there's an imbalance. The object will get pulled up. So what is the acceleration? So the net force, you'll first find the net force in the y direction is equivalent to m times a. I'll call it ay because it's in the y direction. So I like to call it net force in the y direction because that way we are clear whether we are doing y direction problem or whether we are doing x direction problem. So the net force is now Fp, the vector in the upward direction. We'll show the free body diagram for this. Do not solve any problem without showing the free body diagram. Whenever you see a problem, you draw a dot for the box and you show the vector. Also show the length of the vector correctly. And for example, now the normal force, the force of the push is greater. Pull, the rope is pulling with 100 newtons and the weight is only 98 newtons. So the vector for 98 is slightly shorter compared to that one. So upwards means positive, downwards means negative. is equivalent to m times a y, the acceleration. We can find the net force here. We know that the net force is 2 newtons because you're subtracting it, but I would like to find out ay first. What is the acceleration with which it is pulled? So if you rework on this, fp minus mg over m, you substitute 100 for this. 100 minus 98 is 2.0 divided by 10.0 kgs. Okay. And when you work on this, you'll get a tiny acceleration for this block, which is 0.2.0 meters per second square. So it can accelerate only when it exceeds the weight. So there are many, these examples are given in your textbook. You should definitely go and work on these sample examples. So now we'll pause for some time here, and I would want you to do your readings for this part and then come back with information about this entire content. The portions that you should cover before coming to next lab will be section 4.1, 4.2, 4.1 is about introducing your Newton's laws. So I will not be teaching another section today because of your exam, but I would expect you to come back next time learning about 4.1, 4.2, 4.3. 4.1 is just simply defining forces. 4.2 is Newton's first law of motion. 4.3 is talking about mass. And 4.4 is Newton's second law. And this is your Newton's first law, law of inertia. Okay, so this is introduction to forces, 4.1, and 4.5 is Newton's third law. To every action there is equal and opposite reaction. Go ahead, and you have a lot of catch up to do on the work. So I will stop at introduction to free body diagrams, and when we meet in the lab, we will work on free body diagram problems. We also worked on force due to gravity today, that is weight. And so basically most of the introductory stuff is done. You have to work on going through 4.1 through 4.6, and we will pick up from 4.7 working on problems next week.